Okay, let's start. Welcome to the Distinguished Lecture Series. It's my pleasure to introduce Eric Brewer. Professor Eric Brewer is a professor of computer science at UC Berkeley. He focuses on all aspects of internet-based systems, including technology, strategy, and government. As a researcher, he has led projects on scalable servers, search engines, network infrastructure, sensor networks, and security. His current focus is technology for developing regions with projects in India, Ghana, and Uganda, and including communications, health, education, and e-government. In 1996, he co-founded Inktomi Corporation with a Berkeley grad student and helped lead it onto the NASDAQ 100 before it was bought by Yahoo in 2003. In 2000, he founded the Federal Search Foundation. Working with President Clinton, Dr. Brewer helped to create USA.gov, the official portal of the federal government, which launched in September 2000. He has a long list of accolades. He was named a global leader for tomorrow by the World Economic Forum, by the industry standard as the most influential person on the architecture of the internet, by InfoWorld as one of their top 10 innovators, by Technology Review as one of the top 100 most influential people for the 21st century, and by Forbes as one of their 12 e-mavericks, for which he appeared on the cover. He was recently elected to the National Academy of Engineering for leading the development of scalable servers and named an ACM Fellow. And I think most importantly, he was my PhD advisor. So without further ado, Professor Eric Brewer.
Thank you. So I'm going to talk about a topic that doesn't get covered in computer science much, which is development. And I don't mean writing code. I mean actual development as in developing countries. And this is a topic that I feel should be in the realm of computer science because I think computer scientists have something to offer. And if you just kind of take a step back for a minute and say, well, what is the difference between, say, Canada and rural Africa? And one answer would be the presence of technology. Now, it's not exactly, you can't just put the technology there and all things will be equal. But it is the case that I think, in some sense, what development means is to have technology. And so what I'm trying to do is point out that technologists ought to have something to say about that, right? The history of development is essentially a history about macroeconomics and governance, and there's really been no involvement by technologists at all, even though technology is clearly, I think, one of the few tools that can make a difference for developing regions. So I'm going to try and convince you that this is a topic worthy of our attention, and in some sense that this is a community decision. We computer scientists can decide whether this is in our purview or not. It's not up to anyone else. It's up to us, right? So I'm giving this talk in a few places because I believe that we should decide to work on this. I'm going to work on it. I'm happy to say Keshav is one of the few other people working on it at Waterloo. And that hopefully this is the start of something quite significant. The group we're kind of aiming at is often called the base or the bottom of the pyramid, the idea being that there's a pyramid of population and wealth, and if you're in this room, you're at the tippy top of the pyramid, and you have a very high income, relatively speaking, to the average of the planet, and there aren't very many of you. That's why it's a little pyramid, right? At the bottom of the pyramid, which is really a triangle, by the way, is most of the population of the planet, and they make very little money, although there are a lot of them, so in aggregate they have a fair amount of wealth. It's just not much each. So this is quite a large group. It's at least 3 or 4 billion people already. It's the fastest growing part of the pyramid. The pyramid's getting weightier on the bottom, which is not good. This typically is because the population, the birth rates are high in this section. So it's growing quickly. It's a mix of rural poor and urban poor, and I'll talk more about rural and urban issues later. But in general, there's movement of people from rural areas to urban areas, which is overall not a good thing, but we'll talk about why it's happening. Education is low and pretty much non-existent in some parts. There are high discrepancies between education for men and women. In general, if you're a poor family and you can send one of your children to get educated, it's going to be a male child, probably the oldest male. So that's one reason for the discrepancy. Another problem, of course, is there's an issue of say, preferential birth for male children. And you can figure out how that's implemented. And in general, although it's often called the base of the pyramid as if it's some homogeneous market, it's not. It's actually very heterogeneous, and that's one of the problems. And I think one of the keys to the solution is to really appreciate that there is not going to be a solution that is just going to work everywhere. It's going to have to be very much bottom-up and decentralized and localized. So all the technologies I'm going to talk about today, implicitly, I won't say it much, but if you watch for it, you'll see they're all actually things that are appropriate at the village level and can be highly decentralized and can grow upward, bottom-up from there. It's not top-down, we're going to build the great dam and it's going to power the cities. This is quite the opposite. It's small technology, widely deployed. And one of the things that's going to make this possible is money. We're not going to have money top-down from the World Bank, although I think that there's places for that. We're going to get our money actually from Microfinance is one source. I'll talk about another source in a minute. Microfinance is something that pretty much I think all university students need to know about, and it's not uniformly taught, so I'm going to correct that right now. Grameen Bank is one of the founders of this idea. In fact, Muhammad Yunus won the Nobel Peace Prize a few years ago for creating Grameen Bank. And he started this bank essentially because he couldn't get another bank to do what he thought was right. And here's the insight. The insight is, if he loaned money to his poor friends, they would pay him back. If he loaned money to his wealthy friends, they'd forget. Right? It's because, in the same way that I might take you out to dinner or you might take me out to dinner, it's not enough money between us that we really care. So it's not that his wealthy friends were, just intentionally not paying him back. It just wasn't a big deal. But for his poor friends, it was a very big deal, and it was a cherished relationship. And they always paid him back, and in fact, they were hoping for a future loan implicitly by maintaining the relationship. So he started loaning more and more money to his poor friends, and they consistently paid him back. And for them, it had a big impact. Right? For him, it was a small amount of money, $50, $20, but for them, it was an impactful amount of money. So he kept doing this, and he eventually decided he needed to form a bank. The reason he couldn't convince other banks to do this is the somewhat obvious reason, which is the response of a normal bank is, well, these are not collateralized loans, right? They're poor people, they have no collateral, they're not going to pay me back. Why would I make these loans? And the short answer is they will pay you back. They'll in fact pay you back more likely than your regular customers. The repayment rate for Grameen Bank is over 98%. That's much better than a Western bank. That's a little misleading because Western banks intentionally make risky loans that have higher returns. So the Western bank can control that return rate a little bit, and it's artificially lower than it might be. So doing this, $100 at a time, this bank has made many, many loans over many years. Now it's loaned $4 billion out in $100 increments. Just think about how to do that. It's not so easy, but that's what they've done. And they've never taken any money in. So all that $4 billion that they've loaned out is money they've earned in the past from interest on the previous loans. Right. So this is the capital is growing. And at the end of the day, this turns out to be the most effective known technique to get people out of poverty. And this is why I think everyone needs to know about it. The way it works to get people out of poverty is not by giving somebody a small loan. That won't get them out of poverty. How it really works is it's a sequence of loans. So I'll loan you money for a goat. Don't eat the goat. You milk the goat. You use the milk money to pay back the loan. That takes about 3 to 6 months, maybe a year. Then you ask for another loan for a goat, and I give you another loan for a goat. You do the same thing. Now you have 2 goats. After a while, you have a herd. You have some employees. Right? Now you're out of poverty. So it's the sequence of loans that gets you out of poverty. And it's also the sequence of loans that makes the repayment rate so high. The kind of secret of this is that most loans are made to people that have already paid back a loan. Right? So they're not completely untrusted. Right? They have some credibility. Obviously, the first loan was on trust. The other game they play, which I don't have time to get into, is they've now learned who to loan to. And in fact, almost all loans go to women, right? Even though that's, in some sense, I just told you all the male children get educated, all the loans go to women, right? Maybe you can figure out why that is, but I think the root answer seems to be mothers are good loan targets because mothers spend money on their kids, right? Mothers invest for their children. All right, so you're really loaning to mothers is the reason this works. Another reason it works is you tend to loan to a group. And so one person is getting the loan in the group, but the other people in the group can't get their loan until the first loan is paid off. And the consequence of that is it's peer pressure to help get the person who has the loan to pay it off. And in fact, more than peer pressure, it's actually a support group because if that person gets sick, there's a good chance the other people in the group will make the payment for her, because they want to keep the relationship alive with the bank, right? So the group is stable as a loan target. So remarkable system, well deserving of a Nobel Prize. What it means for me and for technology is here is the capital you need to deploy projects in rural areas, right? It is readily available. It is not high overhead. And in fact, you can use it for technology. We'll come back to using it for technology in a little bit. There's another major source of income that people don't know about, which is remittances. So remittances, I'm sure some of the people in the audience, given the diversity of the Toronto area, are actually paying remittances now, whether they know what they're called or not. Remittances are the money you send back to your relatives from your home country, right? And it turns out this money is an incredible amount. So this is per year. For Africa, $40 billion every year flows into Africa in these little bits of money sent home by the relatives, right? That's 10 times the amount the U.S. puts into Africa over a 5-year period, right? The U.S. is very proud of its $4 billion for AIDS. That's a great thing. I'm not, slamming that, but that's a whole lot less than $40 billion sent in little bills home to relatives. So this is, in fact, where this money is what pays for a lot of little projects in villages today. Not necessarily technology projects, but things like fixing the well, or getting a TV, or all kinds of little things. That's what remittances do. They pay for things that are very localized in the village, usually the home village of the person sending the money back. So I bring this up because this is already flowing. This money is not money we need to raise. It's there. It's just not understood very well. So between microfinance and remittances, my point is there's a decentralized flow of money that means we can do decentralized projects without needing a lot of top-down philanthropy. We don't need any philanthropy at all, actually. In fact, nothing I'm going to talk about today is philanthropy. It's all self-sustaining on its own economic viability. Right? Now, philanthropy would be great, too. You could do that also. But you don't need it, and I don't want to depend on it because I want this stuff to be self-sustaining. Right? Philanthropy is fundamentally not self-sustaining. Eventually the money stops, then the projects die. That's not where I want to be. I want to be in projects that are self-sustaining so that when I leave and the money stops flowing, they're still going. Right? That's the goal here. Another piece of background. Maybe the solution is already here because cellular is tremendously successful in these regions. It's 3 billion users already worldwide. This is, I think, pretty easy to claim the most successful technology ever. Right? Certainly touched the most people of any other technology. I mean, maybe you could argue for seeds or something. There's certain seeds that might have touched a lot of people, but I don't think there's any seed that's touched 3 billion people. Right? And in fact, Africa is still the fastest growing cellular market. So it's taking off quite well. There's a couple of things to learn from this. It's certainly important that it's easy to use. It works for any language, any dialect, with no training needed. Right? So that's very important. Voice in general is going to be an important part of all our solutions. It's also important to realize that one of the things driving the cell phone is, in fact, the remittances. I'll talk about Bangladesh in a minute, but the reason poor people in Bangladesh village need a cell phone is actually to arrange money transfers. Right? That's one of the driving applications. Because it's not obvious on the surface why a villager would need a cell phone. There's two main reasons. One is remittances. The other one, which I don't have time to go into, is it turns out most business people were limited in their amount of business by the number of people they could physically bump into, which is not that many people. So a cell phone essentially means it's all the people that you could get to within a, say, 10-kilometer range that might be customers, right? And you're arranging transactions such as like being a plumber is a good example, or most taxi drivers now have cell phones because they can get more customers by having a cell phone. All right, so wildly successful. Maybe that's, we've just solved connectivity. Turns out it's not true, but let's dig in a little deeper. So, Grameen Telecom is related to Grameen Bank, and the idea was, well, instead of making a loan for a goat, let's make a loan for a cell phone. And the way this is going to work is the phone lady, again, it's always ladies, they're called phone ladies, she's going to buy the phone using the loan, and then she's going to rent the phone to her neighbors like a payphone. Right? So you borrow her phone, you make a 5-minute call, you pay her for 5 minutes of time. And she's, of course, paying for 5 minutes of time herself, but she's charging you more than she's being charged. So the income is the difference she charges you for minutes on the cell phone. And again, this scales tremendously well. Right? So 95,000 loans have been made as of, actually, this is about 2 years old. And those 95,000 phone loans now cover about 50,000 villages. Right, so many, many people, their phone that they use is actually the village phone that's operated this way. Right, so tremendous scale. There's a couple things to learn from this. The scale is probably the main one. There's 60 million users who are using this system now. Right, that means it's competitive with other kinds of large-scale cellular providers. And it's really done a good job of covering the rural villages. Almost every rural village has a phone now because of that. It's not everyone. We'll talk about why in a minute. And for the phone lady, it's quite a good deal because the income she makes being the phone lady is on average about double the typical income for her village. So it's much better to be the phone lady than to be a farmer, which is the main job of these villages. But the other part of this is because it's her income and it's a cherished income, she does a whole bunch of stuff to keep the system operating. Right? So most technology projects fail somewhere along the line because there aren't parts available, there aren't people around to keep it running. Well, the phone ladies are the people that keep it running. And even though they aren't actually trained very well to do so, right? They keep it running because it's their income. Right? Just think of it this way. Smart people, highly motivated, right, can keep this system running. So what does that really mean? It means charging the batteries. It means knowing the battery isn't charging correctly and you need to buy a new one and buying it. So actually, in fact, saving enough money to have money to buy a battery before, when you need one. So it can kind of cash flow management. It also means learning dialing codes, even if you might be illiterate. So most phone ladies know calling codes for all the countries that their villagers might call, and maybe even some city codes too. One lady, I actually don't know if the lady did itself, but one of these such phones I found had someone had put an external GSM antenna on a pole in their village and connected the phone to it. Now, I don't know how they knew what a GSM antenna was or where they got it, but the bottom line is these are smart people, and if they need to figure out how to get the phone to work, they'll do it, right? Right. So, pretty surprising. Now, so I've just hopefully convinced you that we can use microfinance to scale a project up, that technology can be used to have, immediate income on at least this woman's income. So we've made 95,000 people wealthier. We've also, of course, made it simpler to do remittances by having these phones at all, and of course increased the relative communication ability of these villages. So in some sense, problem solved, but it turns out it's not quite enough. And the reason for this is that cellular is really an urban phenomenon. And it's pretty fundamental. It's not going to change in the near future. It might change eventually. And the reason is cellular uses a base station model where you have a relatively expensive base station that provides a circle of coverage around that base station. And to be economically viable, you have to make sure you have enough users within the radius of that base station to pay for the cost of the base station. So my definition of rural is essentially low density, low population density. So cellular is in fact deployed successfully pretty much everywhere in the world where there's high user density. right? That's why it's taken off so quickly, because it makes sense. It's not widely deployed in places of low user density. There's a few exceptions. Bangladesh is not one of them, which I'll get to in a minute, even though I just told you it has rural phones. China is the main exception I know, and the reason China is an exception is they decided by fiat that there would be coverage. And when you're a big, powerful government, you can do that. It doesn't have to be economically viable. And it's true. I've been to rural China, and there's some places that are very rural that have very good coverage, much better than U.S. or Canadian coverage. Right? But it's not because it's economically viable. So green telecom, as I mentioned, is not an exception to this. And the reason is the loans pay for the phones. They don't pay for the base stations. So all the base station costs in the green telecom model are essentially subsidized by the middle class users that are paying to use phones all the time. Right. This works in Bangladesh because it's a very dense country. In some sense, the whole country is high density. Right. So it's not representative of most of the world. It's more like Hong Kong, right, that kind of density. And the other reason it works is that it turns out for middle-class users, it's a pretty good idea to cover certain key roads and key rail lines. So basically, the 50,000 villages that are covered are really those that are either next to a city or next to a major rail line. And the 18,000 that do not have coverage are exactly those that are not in range of one of those things. Right, so that's why it stopped at 50,000. Because to do the other 18,000 villages, you're going to have to deploy new base stations, and that's not covered by these costs. You could do it through philanthropy, but you couldn't do it just through these costs. And taking it up a level, one thing I want to point out is this is a general belief, or at least a discussion about the world being flat. And what Thomas Friedman meant by that is that jobs can move fairly easily between Bangalore, India, and Shanghai, China, and Waterloo, for example. But I would refine that and say the urban areas are self-similar, but they're not at all similar to the rural areas. Bangalore is much more like Waterloo than it is like the village next to Bangalore. Right? That, I think, is the important thing. So what we're seeing is that the divide that's going to matter, and the divide I'm going to focus on, is really the urban-rural divide, and I'm going to let the urban issues essentially roughly be handled by industry or by urbanization, right? Which is how cell phones got deployed. It's how lots of things are being deployed now. So in fact, urban changes, not that I'm saying they're unimportant, but I think they're on a road more likely to take care of themselves because of the money flowing into these areas and because of the flatness, right? But the flatness doesn't apply to rural areas, and we're going to need to be more proactive there. So this led me to kind of a hypothesis, which I'm not going to prove today, but the hypothesis is that kind of wireless infrastructure is really the first viable infrastructure for rural areas. Unlike roads and rail and water systems, which are very expensive, they're too expensive for rural areas. Wireless is not too expensive for rural areas. So cellular base stations might be too expensive for rural areas, but that doesn't mean wireless is too expensive. And my hope is that if we get wireless capabilities in rural areas, that alone can lead to other kinds of infrastructure and other kinds of income. And we have seen that cell phones have led to certain kinds of income. So there's some connection in urban areas already. And this is, again, it's a hypothesis. I can't prove this yet. But one of my personal motivations for this kind of work is that I feel like if we can get wireless to these places, we'll make them more viable for other kinds of opportunities and infrastructure. And I think Wi-Fi in particular, because it's low cost, much lower cost than a cellular base station, is a particularly good option. Okay, so I'm not completely disconnected from reality, give you one anecdote about this hypothesis. IT Mountain BPO is a tiny company in rural Kerala that works on medical transcription. So they take audio files and that have what a doctor said, and they turn them into text files. And they started with customers in India, but now they have customers in the US as well. What's interesting about them is they're in very rural Kerala. Kerala is one of the southern states of India, and they're 30 kilometers from a small city, not 30 kilometers from a big city. So they're, as far as cellular coverage, it's non-existent, right? So it turns out they are part of an experimental program in Kerala to have wireless kiosks in rural areas. So in this rural kiosk, they've basically set up this business, and they make about $8 an hour doing this transcription. Well, this is a tremendous amount of money for this rural area. This is by far the best paying job in the area. And so what he's done, he did it because he wanted to live near his home village. So he said, I have wireless now. I can do this work. I can telecommute. I can do this work from home. And that's what he's doing. But now what's more interesting perhaps is the way he does it is he hires actually 3 local people to transcribe the audio. Right? They're not all that educated. They don't do a very good job, at least not at the beginning. They obviously learn on the job. So he has 3 people do it, and then his more senior staff, which used to be him, but now he's got a bigger staff, the senior staff will actually compare the 3 versions and decide how to merge the differences. So it's more efficient with the senior staff time. And of course, that helps correct the mistakes of the junior staff so that they get better over time. So he can afford to translate it 3 times and still be cheaper than having it done in the city. Another funny story about this guy is he kind of got started because in Kerala, they were outsourcing their audio transcription to Bangalore, which is the same thing we do in the US and Canada, right? But Bangalore got too expensive, right? So where does Bangalore outsource its transcription? Well, to rural guys, right? So now the outsourcing from Bangalore, which is now part of the urban flatness, so that's how he got started, is reducing the cost from these expensive guys in Bangalore, which of course are the cheap guys to us. So here, anyway, is an example of real income for many different people, entirely enabled by wireless. And my hypothesis is that if that kind of stuff is enabled and continues, that will bring other kinds of it. That will make the roads better down the road. It will improve the education system. But that money flow is the root. So Wi-Fi enabled rural income. So I'm going to focus on Wi-Fi. We have many different projects, by the way, education and healthcare and things. I'm going to focus today mostly, due to time reasons, on Wi-Fi and healthcare because it's kind of our flagship project. Why Wi-Fi? The main reason is it's super cheap. It's, in fact, not a very good choice for rural connectivity because it goes short distances. Right? You think of Wi-Fi, you probably think a hotspot, 100 feet, 200 feet. That is what it was designed for, and it's very good at that. We're going to use it to go 100 kilometers. And it's not designed for 100 kilometers, but it turns out we can make it work, and I'll show you how we did that. But the reason to use it, even though it wasn't designed for this task, is that it's $5 for a Wi-Fi chipset. Right? 140 million Wi-Fi chipsets were produced in 2005. I don't know the number for more recent years, but it's a huge number. Right? Every laptop now has one. Many phones now have them. So because of the low cost, if we can get it to work, it will be the right choice. It's also a good choice because it works in unlicensed spectrum. I'll come back to this later, but the short version is we don't need the permission of the government typically, explicitly. We don't need to work with a carrier, and we certainly can just do things at the village level quite easily. So that's very important. And also, of course, we don't have to pay for spectrum, which is implicit in that. It fits my decentralized model. We can deploy one village at a time or a group of village. So incrementally growing the network with incremental capital cost. Right? Again, trying to avoid the kind of top-down big capital approach. So start small. If it works, grow over time. If it doesn't work, well, yeah, it doesn't work, but you didn't spend much money on it. Right? So low risk. There's a bunch of variations used in practice. Meshes, which are what are the most common topic in computer science because they're how you might connect an urban area like Waterloo. Like Waterloo might even have a mesh or a partial mesh for all I know. The campus certainly probably does. Wild, which is what we created since for wireless long distance or Wi-Fi long distance. And we'll talk mostly about that. But then there's also hybrids, which I'll talk a little bit about, which is we use long distance links to an area and then use a mesh in that area to provide an island of connectivity. And since people tend to live in islands of population density, that's a pretty important model. So here's the one technical slide, or the most technical slide anyway, which is what did we actually do to make Wi-Fi go over a very long distance? So I should first point out that you can get Wi-Fi signal, RF signal, to go a long distance just by having directional antennas. So I put a big directional antenna on each end. I can get the signal to go a long distance. The problem is the bandwidth. And there's a few things. First thing we had to do is go to TDMA, time division multiplexing. The way regular Wi-Fi works is essentially you listen. If you don't hear anything, you talk. And that basic protocol works quite well if the two endpoints are close together, right? Because what you're listening for really is can the other end hear me? Or is there too much noise? Right? So in a short distance, listening and then talking is a good protocol. For a long distance, it doesn't work. At 100 kilometers, I can listen all I want. I can't hear what's going on at the other end. I have no idea. Right? That's one problem. Another problem is that what I'm hearing is delayed. So I listen now, I don't hear anything, but he may have already started transmitting to me and it's on its way, and fast as light is, it's not fast enough. So we may be talking at the same time. And the farther you get apart, the more likely that is. Next thing we had to do, so basically what we do is finish TDMA, is just agree on what time it is, which we can do a couple different ways, but I'll talk for a while and then you talk for a while. I'll talk for a while, then you talk for a while. So as long as we agree on what time it is, we can divide up the communication that way. So we did that. Another problem with Wi-Fi is that it sends one packet in the air at a time. So send a packet, wait for an acknowledgement. Send a packet, wait for an acknowledgement. Again, that's fine over a short distance because you don't wait very long. Over a long distance, you're waiting for the speed of light twice. And it turns out, as short as that is, that's long enough that you spend too much time waiting. So what we do instead is we're going to send a whole bunch of, when it's my turn to talk, I'm going to talk a lot. And then you're going to tell me when it's your turn to talk, which of the things that I said did you hear? And then you're going to start tell me what you have to say. So that's a bulk acknowledgement. Acknowledge in bulk all the things I told you. And that's going to allow us to keep the channel full all the time. We're going to add some forward error correction, which is a kind of redundancy so that we can deal with certain kinds of errors. And then, and this is, I think, the most subtle one, we're actually going to allow two antennas on the same pole to use the same channel at the same time, which on the surface of it is not possible because they'll interfere with each other. Right? Just like two people talking at the same time in the same place are going to interfere with each other. The secret is to give each of them a megaphone and make them point in different directions and make them talk at the same time or listen at the same time. So it turns out if we're both talking, our respective receivers can hear us because the megaphone's pointed at them and not at the other receiver. Right? So the directionality means the receivers hear different things, and so even though we're both talking and it might sound like a mess locally, at the receivers it's clear. Conversely, if we're both listening and we have our kind of inverse megaphones listening, right, then we're getting much more signal from the direction we're listening to than from the direction we're not listening to, and we can differentiate those signals. The only case that doesn't work is if one is talking and one is listening, in which case the noise from the talker drowns out the remote sound you're listening for. So because we're already using TDMA to synchronize slots, as long as we agree on the time for both of the radios on the pole, then now they can both talk at the same time and both listen at the same time. So what that means in practice is we get to use two channels in the same frequency at the same time with no penalty. We're going to get the full bandwidth on both links, even though in theory that's not possible. So it's free spectrum essentially. And you can do this multiple times. You need about 12 dB difference between the directions. So we know you can do at least 6 links at the same time using that because you need at least 60-degree separation. All right, and we're also working on future versions for point-to-multipoint and for better handling of VoIP, which I won't talk about. So this set of graphs basically just shows, this was a simulation of regular Wi-Fi over long distances. So this is 100 kilometers, and this is normal bandwidth. So normal 802.11b Wi-Fi would be at 6 megabits per second. This kind of just shows what you get with regular Wi-Fi. Roughly, I guess I can explain what's going on. This slow drop is due to the round-trip delay getting longer and longer and spending more and more of your time waiting for the acknowledgement. This drop is due to the fact that at some point the acknowledgement timer times out and says, oh, I give up waiting to hear this, I'll retransmit. So it retransmits 3 times, and then it gives up and moves on to the next packet. So about a 2/3 drop in bandwidth because it's sending each packet 3 times now before it gives up and moves on to the next packet. And then some continued dwindling due to utilization. This is the emulated tiered Wi-Fi link that we built using all the techniques I just told you about. And then this is actual links. The squares are tier links and the circles are regular Wi-Fi. And they do, in fact, generally speaking, match relatively well. The important point is tiers generally getting good bandwidth across the range of links. And the one on the far end is pretty important. That's 382 kilometers. Again, this is one hop. It's not multi-hop. One hop, no amplifiers. Right? Just a regular Wi-Fi card on each end, passive antennas, and that's it. Right? So there's the picture of it. We cheated a little. We cheated by being at 4,200 meters. Right? The problem with this distance is that the Earth curves. Right? So you need to get to a place that's high enough where you can see this long. But the mental picture I want you to have is if you can see it, we can connect it. All right? It is really, we are not limited by the distance. We are limited by how far we can see. Right? Which is usually a curvature of the Earth problem. This is about a 30 dB antenna. So this is a big passive antenna. I'll show you other antennas in a minute. For that kind of distance, you need a big antenna. For typical distances, you can use a small antenna. So we've done a few projects with this. The first one I'll talk about is a rural ISP. So this is in northern India in Dharamsala. Dharamsala is the place where what used to be Tibet now lives. When Tibet wasn't, you can decide on the verb you want to use, but when the previous Tibetan government was asked to leave, they went to India. And they went to this town called Dharamsala, which is where this is. So this is in the Himalayan mountains and foothills. So it's very mountainous, and it's very rural. And so basically all these places are villages in this area, and then there's some amount of relay stations where we're using a mix of kind of short links and long links. But the bottom line is these are real links deployed with about 10,000 users, and most users essentially are using this for VoIP and for internet access. So it's not that they have it in their house, but they'll go to an internet cafe or a school or a building in their village, and that building has computers in it, and it's connected to this network. And then somewhere in the network, which I think is this House of Peace, which is near the Dalai Lama's house, is an actual internet connection paid for from the government of India. So it's essentially, you can think of it as like a shared DSL line that we're then spreading out to a whole bunch of villages using what's essentially an intranet. And you'll see this pattern again. These are quite cheap. These are, $50 to $140 depending on the configuration. So, real users actually used every day. Our kind of flagship project, though, has been using these links for rural telemedicine. This is in southern India with the Aravind Eye Hospital. And in fact, this is a more typical antenna. This is basically a 30-foot pole with a Linux router in an outdoor enclosure, a little pigtail, and then a 24 dB parabolic antenna. There's one cable, which is the power over Ethernet cable. So it's carrying Ethernet and it's carrying power. And that's pretty much it for the equipment. Then, of course, there's one on the other end. So Aravind Eye Hospital is pretty remarkable. They are a high-volume healthcare hospital. What they do basically is rural eye care. They only do eye care. I believe they had about 2 million patients last year. They did about 280,000 cataract surgeries, right, just last year. Right? So very high volume, and they focus on the poor. So 2/3 of those that got cataract surgery got the surgery for free. Right? And that was paid for by the other third. Right? So it's not that this is not philanthropy. The paying customers are paying for really 3 surgeries, theirs and 2 other people's. Right? And this works because they've made the cost of the surgery so low that paying for 3 people's surgery at Aravind is cheaper than paying for a regular surgery elsewhere. Right? In fact, it's cheaper to fly to India and get your cataract surgery done here than it is to have it done in Canada to the U.S. Modulo insurance in Canada. Right? Assuming you were paying for it, it would be cheaper to fly. So there's a huge need in India for this. And what they found in looking at their hospitals is that they were really quite limited by who could walk, maybe occasionally take a bus. But the bottom line is all their patients were coming from relatively nearby the hospital. And that's a problem because they don't want to build hospitals with, at every village, right, or every kind of district. So the goal was to build 50 rural vision centers, and then we're going to use these links to connect them. So this was the network we put in, the first 5. These are relatively short links because, again, at the time we put these in, we didn't actually know how far the links would work, right? So we had to be conservative, pick short links. But there's still long distances for Wi-Fi. It's 15 kilometers. You wouldn't do very well on regular Wi-Fi at that distance. All of the links are actually having quite good bandwidth. You can use relays, so there's a couple relay points here. They work fine. They don't seem to affect the bandwidth much. Obviously, they affect the cost a little bit because you need more radios. And this is used about 3,000 times a month, and actually I just got new numbers. It's now about 5,000 times a month. So 5,000 times a month, we have this kind of video conference center used. This is usually 1 or 2 rooms. It has the PC, the webcam, and the microphone. Usually has one nurse, is this woman, and she's kind of not a nurse in the Western sense. She's really a kind of local girl trained for eye care. So she's the administrator. She knows a fair amount about, administering eye care. Like she probably can recognize bad cataracts at least. She does glucose testing. She's the pharmacist. She can dispense antibiotics if the doctor tells her to. But not a fully, if you asked her about anatomy, she wouldn't know, right? So it's just narrowly trained, but 3 months, 6 months of training. And most patients typically, they have a slit lamp lens, which is the kind of normal thing you would have seen a doctor here. But that's it. Really, the actual interaction is you go in, you talk to the nurse, she decides if you should talk to the doctor, then you'll get on the video conference, she'll tell the doctor the real basics, and then the doctor will talk to the patient. And that usually lasts about 5 minutes, and then that's it. And the doctor will make some diagnosis and tell the patient what to do. It could be take these antibiotics that she's going to give you. It could be you need to have cataract surgery, and the nurse will give the person a card, and then they'll go to the hospital later and get the surgery. But there's a few subtle things in this interaction. One important thing is that the video matters because doctors in these areas are used to doing most of their medicine by interviewing, right? Because they don't have a lot of tools. There's no lab. You don't go get the labs done, right? So the doctor really depends on the interview as the primary method of diagnosis. And the video interview, as you can imagine, is much richer than an audio interview, right? You get a whole bunch of extra information that matters. And this, by the way, again, we're running it at 6 megabits per second. So we only need a megabit per second to have a very high quality video conference. So the patients view it as TV, and they call it the TV. The doctor's on the TV, right? And that's not a bad way for you to think about it because from the patient's perspective, it is not a complicated technology. The screen is on all the time. It's a TV, and they see the doctor in the TV, and they just talk to him. It's two-way interactive, but that's the only thing that's odd about it to the patient. Right? They've usually seen TV or at least cinema before. The other important thing is that if the doctor tells the patient to do something, the patient is much more likely to do it than if the nurse tells the patient the same information. So the credibility of the doctor is important, and part of it, this is a little bit subtle, is this does tend to actually be a local girl. So it might be that some of the patients actually know the nurse, because this is a small town effect, in which case they really don't listen to her, right? She has no credibility with them, right? I mean, she might be a smart girl, but that's Fred's daughter. She's no eye care, right? So, but the doctor, even if he says the same thing, that's taken seriously. So this has had quite a real impact. This is certainly, I think, our flagship project. Over 80,000 patients have used this system so far. And again, this is not philanthropy. These centers are self-sustaining. Their income, in this case, comes from selling eyeglasses, from selling antibiotics. They do actually sell appointments. I believe the current price is about 25 cents for 3 appointments. They sell you 3 at a time because otherwise you won't come back for your follow-ups. Right? So you're basically prepaying for follow-ups. And follow-ups are actually an important part in some, depending on what it is. So that's not a lot of money, but it's enough to cover the cost of the centers. The links, by the way, cost about $18 a year to maintain and about $6 a year in electricity. So they're very, very low cost. This is, if you get one number from this talk, this is it. 14,000 people can see today that couldn't see before. Right? And it's not because they couldn't get treated before, it's because they weren't diagnosed and they had no access to eye care. Right? So it's not that me or my students did the cataract surgeries or gave them special astigmatism glasses, which are the 2 most common causes. It's that we allowed them to get diagnosed and to find out that what they had was treatable. The guy on the right here, whose name I don't know, because in a high-volume hospital they don't deal with names. I'd like to know his name. I'm still trying to learn it. He was blind for 7 years, treatable the entire time. Right? He just didn't know what he had was treatable, and he didn't know that it. In fact, if he had walked into that hospital any time in the past 7 years, he could have gotten treated, including surgery, for free. He didn't know, right? Right. And this is, again, 7% of the rural population has access to eye care, so he's not alone, right? The majority of people in rural India do not have any access to eye care. In fact, the way to think about it, there might be, even if there was a doctor in their village, he probably wouldn't treat most of the people in the village, because he's probably in private practice. Right? They can't afford him. Right? So access to eye care is the value of this. And by the way, as you might imagine, there's nothing here that's specific to eye care. Right? We did this because it was an eye hospital, but this would work just fine for all kinds of medicine. Again, especially because most medicine in these places is practiced by interview. Right? It's not. We can put equipment here like this. We can actually send JPEG images from the slit lens over the network. We can send vital signs. None of that really gets used because the interview is the important part. But, you know, the rest is, we thought it would be important. We did it. I think it has some value. So we're at 24 centers now. This is going to grow to 50 when it's done, which will hopefully be in the next year. At that level, the catchment area is what it's called. It'll be about 2.5 million people. And then we're hoping to expand this to Nepal and to Pakistan in the next maybe 18 months. So we'll see where that goes. So hopefully I've convinced you that there's a role for technology to play, that there's money to do it, that the village is a natural thing to focus on, and that even in rural villages, you can get stuff deployed that has impact. But there are a lot of problems. I want to cover some of the problems, both because I think these are research challenges that are open to our community, and just to point out that, you know, there's a whole bunch of stuff we had to do that I haven't talked about, and there's a lot of stuff remaining. So we've had this system up for a couple of years now, and we can kind of understand why it fails when it fails. And I'm not going to go through all these, but one obvious observation that came out with is almost all failures were power related. 90% of the failures, we kept a log of why things broke, and the answer is power most of the time. And I'll walk through the reasons. Well, then we went and measured the power in rural villages. There's 2 different villages in India. And this is supposed to be 220 volts AC, right? So this is the number of times in 6 weeks that it was wildly over and potentially with the wrong phase, right? So if you plug your laptop into a 1,000-volt socket, it will not survive. You just lost your power supply, right? You plug your cell phone charger into that, and you get a 1,000-volt spike. You just lost your cell phone adapter, right? So that cost us, it turns out, was the root cause between losing about 50 power adapters and about 30 point of power over Ethernet ports. So I showed you that cable carried power up to the radio board. Well, if the root power gets a big spike, in many cases it just passes that right through the power over Ethernet injector, up the cable, and fries the port, the Ethernet port. Now, fortunately, they came with like 4 Ethernet ports, so you could burn 3 before you had to throw the board out. But eventually, you lose the board. Low voltage, it turns out, which I don't have on the graph, is equally interesting. when you have low voltages, so a lot of times we'd see voltages that are like 70 volts. It's supposed to, again, it's supposed to be 220. If you try to boot a machine at low voltage, it'll hang. So it'll boot up partially and stop. And that's bad because then someone has to go reboot it. So in fact, early in our work, we were working with some kiosks in a different part of India, and their regular ritual was every morning they would boot up turn on the literally big power switch, the kind you see in the movies, that would turn on power to all the machines. They would all hang, and they would go and reboot each one individually. And they did that every day. And we were trying to figure out, why do all the machines hang? Well, the answer was, when you put on all the power at once, all the power gets sucked into the magnets of the CRTs of the displays. That drops the power voltage down, and then the machines don't boot correctly. So in fact, the solution to that is to turn on the CRTs and the PC separately, and then you don't have that problem. In our case, the problem is the grid power is too low coming in, and the machine boots. So the answer to that usually is to have what's called a hardware watchdog, which is a coprocessor whose sole job it is to watch the main processor, and if the main processor seems stuck, to reboot it. Right? Otherwise, the person has to reboot it, which of course doesn't happen. What we do instead is we wait for the next power outage, and that would reboot it for us. Well, that's a terrible recovery plan. So what we do, so it turns out the hardware watchdog will also hang. So what you need is a watchdog for the watchdog, and that's essentially what we built. But the one we built now is an analog RC circuit that has no computers involved, and it's $2, so it's also much more reliable. Another problem with power is that when the power is going on and off frequently, and this is we did see, it tends to do two bad things. It tends to cause the compact flash to get corrupted because you're interrupting writes, and every time you interrupt a write, there's some probability you're going to corrupt the thing it was writing. Right, and particularly if you're rebooting a lot and you're writing on boot, it's just a matter of time before you corrupt the flash. And then you have to go visit the node to replace the flash. Right? In the big picture, it should be obvious the goal here is to not visit nodes. Right? If you visit nodes, especially the ones you have to backpack into, it's not good. Right? That's a lose. And also, these fluctuations damage the battery. So typically, the power is connected directly into the battery gets beaten up, and then the battery life is very short. So what about UPSs? Well, all the problems I just told you about were with a UPS in place. Right? This is not, we didn't forget the UPS. We used the UPS. And this is a bit surprising because UPS is supposed to fix this problem, and it doesn't, at least at the price range we're talking about. Higher-end UPSs can fix this. A low-cost UPS is a standby UPS. And what that means is when the power is on, it passes the power through essentially unchanged. So all the bad stuff just goes right on through and just fries whatever's out there. And occasionally fries the UPS too, by the way. So the irony is that the way to get good power is to have an outage. Because when you have an outage, you're running off the battery of the UPS, and then things run fine. Because the battery produces nice, clean power. Right. So the real answer is to get a better UPS. But all the problems I showed you, and all the problems we had in Aravind, always were UPS was in place. So we did a few things. We built this low voltage disconnect circuit, which basically says if the power is below a certain threshold, then just cut the power to zero. It's a very simple circuit, but that basically keeps the routers out of this trying to boot in low voltage. That helps a lot. It also reduces the amount of fluctuations because when you're in the bad power state, you tend to stay at zero until the power stabilizes and come back. So you just reboot less often. We've also built a low-cost solar power controller because, again, I said some of these relay stations are in rural areas that have no electricity, so you need to bring power to them. Solar is the easiest way. And I'm not going to cover this board in detail, but this is a board that's pretty clever about charging batteries, and you can actually, using the router, you can check on the battery in the panel over the network. So we can do remote monitoring of the power system as well as remote monitoring of the network. And since we did this, we haven't lost any routers. So these two techniques have been pretty successful. And we're also working on a combined version that basically will replace the UPS. So a low-cost UPS that can tolerate this kind of environment. Because it's not actually rocket science to do that. It's that UPSs are not designed for this environment. For example, the APC UPSs typically will not work below 180 volts for a 220 UPS, right? But I know that the power is below 180 volts a whole bunch of the time, right? So that is just categorically not going to work. Another topic to talk about is training. When we started, all aspects of this thing were done by us. The design, the maintenance, the actual installation, that first set of 5 things I talked about, we actually installed those, literally we, like me and my grad students. We bought the equipment, we sent it, or usually actually carried it in suitcases to India, which is safer. And that's not sustainable, right? I've told you before, this is not philanthropy. I want to be able to leave and not send any more money and have the project continue, right? So under that metric, I have to have basically things locally operated. So we had a plan, and I think it's worked out relatively well, which is over time, we migrate different pieces of running the system to local staff. And I would say that part's not that novel. I think the part that's somewhat novel and interesting is we've added one other element, which is this idea of using local vendors. So what happens now is for the normal diagnostics, there's a web interface, and the hospital IT staff, which is not super well trained but knows something, can use that interface to do a lot of the basic problems. And they can tell if a link's down, is it down because the power's out or because maybe the antenna's misaligned, that kind of stuff they can do. Big stuff like installing new links or realigning an antenna or a board seems to be fried, they can't do. And for that, there's a third party, which is an Indian company that does that. But the hospital pays them to do that, right? So even though the hospital staff probably can't get the training to do all the things we need to do, there are other entities in the ecosystem. So the idea is pay somebody who's already in the ecosystem to do the work that's not very natural for the hospital. And that's worked out really well. So when I say a link costs $18 a link to maintain, I know that because that's what the hospital pays this third party to do link maintenance every year, $18 per link per year, right? Plus the cost, if the board burns out, then you got to pay for the board replacement too. But the model is the ecosystem has to be stable to handle it, not the actual hospital. And that's a subtle but important difference because the ecosystem is actually quite a bit more competent than any particular institution. And by the way, in this transition, we also had 5 more clinics, and now we actually are up at 24 clinics. So we did the first 5 clinics, but the last 19, the last 10 for sure had no intervention by us at all. And the other 9 in the middle had some intervention, but mostly not by us, right? But certainly the last 10, we weren't there. We didn't pay for them, we didn't do them, right? They were done, paid for by the hospital because it's self-sustaining. Right, and that's the metric here. Remote management, as I mentioned, is really hard, and we're working on a bunch of solutions for this. This is actually one of my current PhD students. His dissertation is really about how do you make these things easier to remote manage. I'm not going to cover this much other than to say it's still an open problem. We are doing some things interesting. Some places where there is some cell coverage, we're using a cellular modem as a back channel into the network, which means that if that particular link gets done, we can reach the other side of the network, albeit at low bandwidth, in order to do remote login, typically SSH, over the cell network into that node, then from there into other parts of the network. So the way it works typically is you get to one node, and then you essentially go link by link SSHing into each hop until you get to the node that's broken. So it's not elegant, but it does work. And of course, trying to do prevention, for example, one problem we've noticed is it's hard to get high-quality Ethernet cables in India or Africa, which means that over time, if they're in the sun, they disintegrate. And what you see is, as the cable disintegrates, you get more and more bit errors on the Ethernet cable. All right, so if you're monitoring the error rate on the Ethernet cable, you can see that it's degrading before it fails. Right, so the idea is let's watch certain things like the pigtail or the antenna alignment and the Ethernet cable, and when the error rates start to go up, that means we need to replace them. But that's useful to know because it's much easier to replace something sometime in the next few months when you happen to be in the area versus the system's down and it's going to stay down until you replace it, which is expensive and stressful. So prevention is really about can we fix things while we're there anyway. Open spectrum, I said, matters quite a bit, and I want to talk about it a little bit. The root problem here, and this is more Africa than India, but even India has some of these problems, is that most African countries have essentially no telecoms competition. They might in the mobile space, but not in the general space. And it turns out that telecoms have disproportionate power because they pay a very large fraction of the national taxes. For a while in this decade, I believe Rwanda Telecom was paying something like 1/3 of the income of the Rwandan government. So if you're in the government and 1/3 of your tax base tells you to do something, you probably tend to do it. Right? And by the way, when you have this much money, as the telecoms do, if you don't like the government, you can kind of change it. That's not an option that's out of the realm of possibility. So because of this general systemic problem, these countries tend to have weak regulators. And so they tend to be not that in favor of voice over IP in particular, which they know is bad for their business. They tend not to understand data as much, which is good for us, at least in the short term. But they tend to be worried about open spectrum. So it does need to be pushed on. But I think the bigger conclusion we have is that it's not the cost of the spectrum that's the problem. It's the fact that the people that own the spectrum, the carriers, usually the monopoly telecoms, don't really care about rural areas, right? Because in their mind, there's not much money there. So the big advantage of using unlicensed spectrum is not that it's cheaper, it's that it's something you can do now without waiting for the carrier to be involved. Because the carriers, we've waited for carriers in the past, and guess what? They don't come. It's a long wait, right? So in fact, Aravind had tried to do some telemedicine before using licensed spectrum, and it worked in one area where the carrier had coverage, but another area where they wanted to put a center, the carrier didn't have coverage, and the carrier just declined to add coverage. It wasn't in their interest. So that was the end of that center, right? Moving to open spectrum meant we could put centers wherever we want, whenever we want. And that freedom is the important part of open spectrum. And in particular, I think Wi-Fi is the right place to focus on open spectrum, again, because of the cost, and also because, a little bit subtly, a lot of the Wi-Fi equipment has actually been designed for consumer use, and therefore it's actually more reliable and also tends to already have things like web interfaces that need less training than most networking equipment. Right? So if you try to operate a microwave link versus these Wi-Fi links, one thing you'd realize is the Wi-Fi link is much easier to operate because it's been designed with relatively unsophisticated users in mind. Right? And that makes a big practical difference. So I'm not going to talk about other technologies other than just to say we have a bunch of other stuff we've worked on. Here's two of them. Delay-tolerant networking, which Cheriton has certainly done a lot of great work on. This is essentially how do you get applications to work over networks where you don't have a connection end-to-end, which is remarkably common in these areas. In the case of Wi-Fi, we built a working end-to-end connection, but that took a lot of work. Most cases, you have intermittent connections either because the network is intermittent or because the power is intermittent, and therefore the network is intermittent. Right? So there's a whole bunch of work on how to design applications for that. A whole bunch of work on how to use cell phones not as phones, but as essentially as computers. Right? Cell phones are computers, some more than others. Right? But they are the platform for Africa for sure, as terms of how things should get deployed. So in general, we're doing a lot of work on can you do health records on phones? Can you teach English using a phone? The answer seems to be yes, at least at the primary school level. We're working on voice messaging phones. The idea of this is it's a phone, but when you're out of coverage, you can send and receive, you can basically leave voice messages on your phone. And when you get into coverage sometime later, it'll send the message in the background. So it works kind of like SMS, except that it's voice, which for illiterate users is a very, very big advantage. And it turns out for other reasons that the voice messages are much cheaper to the operator than live voice calls. So we expect the per minute rate of a voice message to be 1/10 or less of the per minute rate of regular calls. The root reason for that is that voice messages can be sent when the network is idle, which means there's no marginal cost to the operator to add these messages to their network. Right? Zero marginal cost. So I'm going to wrap up and then take some questions. We have till 6, about 10 more minutes. I think this is, wireless in particular, a potential revolution for development. It's not the only thing going on. I think the microfinance remittances, which, by the way, are enabled by communications, are other important things going on. But these three together, in my mind, mean that the time is right to really try and allow decentralized projects that make sense for rural areas to just be tried. We'll try a whole bunch in parallel. They don't, by definition, they don't cost much to try. Right? And some of them will catch fire and grow. I hope that the rural telemedicine is one of those that catches fire and grows. It's too early to tell, right? But the opportunity is there. There's a whole bunch of stuff to work on, but I think the bigger message is technology has a role to play, therefore technologists have a role to play. There are, to first order, no technologists in the World Bank or the IMF or the Asian Development Bank or any agency that's traditionally done development. Right? Actually, the Canadian one might be an exception to that, but that's rare. Right? But in general, development is done without any understanding of technology whatsoever. And that can't possibly be the right way to do it. Right? And I think it's up to us to decide if we want to be involved, but I think the answer is should be yes, and I think it's a fun area to work on. And I encourage you to join Keshav and others. And plus you get to go to a bunch of cool places. All right, so with that, I'll stop and take some questions.